This is episode 2 of a 5-part series meant to go over 2 proposals to make new buildings cleaner and more energy efficient. Thanks for continuing on. My name is Hugo Wong and I work at the Building and Safety Standards branch, part of the Government of British Columbia, which is responsible for building codes and standards. This episode will go over some key concepts about energy efficiency, greenhouse gas emissions, and buildings, which will provide some context for the building code proposals. If you're already familiar with these concepts, you can move on to episode 3, as this episode will not cover the specific code language, just general concepts. This is a short introduction of about 15 minutes, so it won't cover each concept in depth, but it's meant to get you up to speed enough to broadly understand the effects of the proposed building code language. As this presentation will contain a lot of technical concepts, feel free to pause and give yourself a break at any point. If you need to rewind and listen, or watch it again, you can do that too. It's helpful to first understand what the building code does and doesn't regulate. While it's true that building codes regulate buildings as a thing, it's more accurate to say that building codes regulate building as an activity, so the verb rather than the noun. That means building codes generally don't regulate the operation of buildings after they're built. Building codes regulate individual buildings, but they don't regulate how land is used or how buildings look, which is also known as form and character. The BC Building Code regulates energy efficiency today, and we're hoping to add greenhouse gases to that list. But they don't regulate energy choice, so you could use any number of energy sources like electricity, low-carbon gaseous fuels, district energy, or other options as long as the proposed building meets the targets. As a reminder, the proposed code language would increase the minimum energy efficiency of most new buildings in BC by 20%, similar to Step 3 for Part 9 buildings and Step 2 for Part 3 buildings. That means more people will be using these concepts and procedures in their daily work. At this point, I'll go over some of the important concepts and procedures currently used for step code buildings. Procedures that will become more common if minimum energy efficiency requirements increase. The concepts are part of a field called building science, which studies how all the systems of a building work together and interact, instead of systems in isolation from each other. I'll use a typical single-family home as an example, but the concepts are the same whether it's a home, apartment, or commercial building. These are the basics of energy efficiency in a nutshell. Boost insulation, ventilate smartly, mind your machines, minimize thermal bridges, seal it up, and think about windows and doors. A builder who carefully considers each of these concepts will likely build a cost-effective and energy-efficient home. This slide is from a longer presentation on this topic, so anyone looking to learn more about this topic can click the link on the PowerPoint for more details. This approach is called an envelope-first approach, which puts greater emphasis on a building's walls, windows, doors, roof, and foundation, instead of relying on efficient mechanical equipment for energy conservation. The envelope-first approach is a good one because a home designed to maintain a more constant, comfortable temperature doesn't need to rely so much on heating to keep the temperature up, which reduces the cost of the energy bill and means the buyer doesn't have to spend money on more powerful heating equipment in the first place. If required, heat recovery or energy recovery ventilators can bring fresh air into the building and pre-warm it with heat from stale air leaving the home, which saves even more energy. Specifying more insulation in walls, floors, the roof, and the foundation will keep that heat in. An envelope-first approach also requires workers to pay attention to air sealing so there are no air leaks from little screw holes, pipes, and the like, as well as less thermal bridging. A thermal bridge happens when a part of the building envelope that is more conductive than the surrounding elements provides a path of least resistance for heat to escape from the building. If you've ever felt a cold floor near a balcony, that's due to a thermal bridge, which created a path for heat to move from the inside to the outside. Detail-oriented construction practices can address both. Besides energy efficiency, buildings with good envelopes are more resilient in emergencies and can maintain acceptable indoor temperatures for longer if there's a power outage or mechanical failure. Now that we've talked about energy efficiency as it relates to designing and building a home, I want to address one more thing, the energy modeling phase, which may be a new concept. Before the construction phase, the current BC Energy Step Code relies on energy modeling and airtightness testing to provide the data and insights that help build a cost-effective, energy-efficient home. If minimum energy efficiency requirements increase, these procedures will be a more common practice across BC. For small buildings, an energy advisor or energy modeler is a consultant who can provide energy modeling and airtightness testing services. The difference between an energy advisor and an energy modeler is that an energy advisor, or EA, is registered to a service organization licensed by Natural Resources Canada, and can use the EnerGuide rating system and related software. An energy modeler performs similar work, but may not be affiliated with a service organization or the EnerGuide rating system. Although both are acceptable for meeting the BC Energy Step Code, certain rebate programs may require you to work with an energy advisor in order to qualify. Architects, engineers, or other design professionals may do this work for large buildings, but although the specifics are different, the general concepts are similar. Now let's quickly go over what an energy model, an air tightness test, actually involves. Before a building's built, the EA, or energy modeler, creates an energy model on a computer. They'll input the size and shape of the particular building, the local climate, the insulative effect of walls, ceilings, windows, and doors, and the equipment that provides heat and hot water to the house. The software then calculates how much energy the proposed building is expected to use. The model doesn't include lighting, appliances, and other devices a person plugs in, as these electrical demands vary depending on how an occupant uses a building, which can vary in many situations. During and after construction, the energy advisor or modeler will visit the build site and perform an air tightness test, where a laptop is connected to a blower door fan which covers the whole front door of a building. As the fan runs, it increases and decreases the air pressure inside the house in a controlled way, which reveals any holes in the building envelope and thus the true air tightness of the building. They can report the results to the builder and indicate whether they met the air tightness requirement for any particular step of the step code, or whether more work needs to be done to seal up any gaps. The more gaps that are sealed, the less drafty a building is. As you saw in the earlier slide, each system and decision in a home can affect its energy performance. Changes to one system may affect another. If someone were to try and modify an existing design for energy efficiency by, for example, adding more insulation or better windows, they could be spending more than they need to. That's why we suggest everyone follows what's called an integrated design process, which involves engaging the builder as well as the designers, mechanical contractor, energy advisor, and the client at the conceptual design stage, well before actual construction starts. Collaborating on the design early can optimize performance, cost, occupant comfort, and resilience of a residential building. This isn't a requirement, just a recommendation. Two key goals of this building code proposal are to reduce energy use and increase air tightness. With that context, we should go over a few terms that describe the actual energy efficiency metrics we're proposing for most new buildings in BC. Metrics that are already in use for Energy Step Code. Thermal energy demand intensity, or TEDI, represents the amount of heating energy required to keep a building at a certain temperature, which considers energy losses through a building's envelope, ventilation, and energy gains from sources like the sun's heat or body heat from the people inside. The higher a TEDI value is, the more heat is required to keep a building at a comfortable temperature. TUI stands for Total Energy Use Intensity, and MUI stands for Mechanical Energy Use Intensity. Both refer to the total energy used by major building systems such as heating, cooling, domestic hot water, elevating devices, etc. But TUI is used for large buildings, whereas MUI is used for small ones. Put another way, large buildings must meet both TEDI and TUI targets, whereas small buildings must meet TEDI and MUI targets. Evaluating the energy used for all systems as well as the energy used for just space heating ensures that the building is energy efficient in a holistic way. Finally, percent lower than reference house, sometimes called percent better, compares the proposed building's mechanical energy use intensity to that of a reference building, which is a hypothetical building of the same design, but one that meets a set of minimum prescriptive requirements instead of the actual specifications. This option for Part 9 buildings may be used instead of MUI as an alternate compliance path. While controlling energy use is important for energy efficiency, having an airtight building is important too. Air transports heat energy, and the more warm air that escapes from your home, the longer your heater has to stay on to keep it warm. In addition, air carries contaminants like dust and pollen, as well as moisture, so a home that controls the movement of air keeps homes drier and indoor air cleaner. Improving air tightness is also the most cost-effective way to improve a building's energy efficiency. In the past, building codes and standards focused on the air permeance of individual materials and components like windows and doors rather than the building as a whole. The expectation was if airtight materials were used to construct the building's enclosure, then the end result would be airtight. However, the majority of air leaks occur at joints and interfaces between these air barrier elements. I'll briefly go over air tightness terminology, which is already part of the BC Energy Step Code, but could be a minimum requirement for all communities using the BC Building Code. All three calculate airtightness, but each has a different formula. Air changes per hour, or ACH, is the most common method of quantifying airtightness for Part 9 buildings. Important note, if a home is rated to say 2 ACH, that doesn't necessarily mean that all the air in the home is replaced 2 times per hour under normal conditions. It just means that when the blower door fan is pushing air into the house and increasing the air pressure inside, that figure is just a proxy for how airtight a home is, and it's a method of comparing houses to a common baseline. In the current building code, ACH 50 is the only acceptable method for quantifying airtightness for Part 9 buildings. However, we're proposing to add 2 more methods, NLR and NLA. Normalized air leakage rate, or NLR, and normalized leakage area, or NLA, are calculated by more complex formulas which I won't go over here. However, the addition of these 2 metrics are designed to make it easier for small homes to meet the test. A very airtight small home could have a higher ACH than a leakier, larger home. Introducing these 2 additional metrics are intended to level out the playing field a bit. This information was summarized from the Illustrated Guide to Achieving Airtight Buildings. To learn more about any of these concepts, please click the link in the PowerPoint slide. Let's move on to reducing greenhouse gases, otherwise known as GHGs, or more casually, carbon. We're about halfway through, so if you want to take a break, now's a good time. As of summer 2022, the code does not mention GHG reductions directly, just energy efficiency. But we hope to introduce GHG levels to help the construction industry reduce operational emissions in a more standardized way. We're hoping to structure it similarly to STEP code, where local governments could choose a measure-only level, or medium, low, and finally zero carbon ready. I'll go over some suggestions on how to meet these requirements when we get into the specific building types, but let's just go over some basic concepts now. Making a building more energy efficient indirectly reduces a building's GHG emissions, especially when using more carbon-intensive fuels. The less energy used to make a building comfortable, the less pollution goes into the atmosphere. An energy-efficient building is also a more affordable building to operate, because the less energy you use, the more affordable your energy bill is. This is doubly important when trying to reduce emissions, because a building that's decarbonized but isn't energy efficient could be expensive to operate. What's important to note is that this proposal is focused on GHGs, not energy sources. You can reduce greenhouse gases by swapping existing high-carbon fuels with other energy sources, like hydroelectricity or low-carbon gaseous fuels. Let's go over some terminology. I'll start with the word carbon. Over time, the term carbon or carbon pollution has become a shorthand for greenhouse gas, as carbon dioxide is by far the most common greenhouse gas. In the context of buildings, carbon pollution can come from using appliances like furnaces, hot water heaters, and stoves. Operational carbon refers to emissions produced by a building after it's built, whereas embodied carbon refers to the emissions from a building's whole life cycle, including the emissions from the manufacturing of all the materials used to build the building, the operation of the building, and finally the eventual decomposition of the building materials after it's deconstructed or demolished. To be clear, this BC Building Code proposal addresses operational carbon, not embodied carbon. Other strategies, such as choosing materials low in embodied carbon, can address that issue. Other greenhouse gases like methane, nitrous oxide, hydrofluorocarbons, perfluorocarbons, and sulfur hexafluoride cause tens or thousands of times more global warming by weight than carbon dioxide, but they tend to be released in far smaller amounts. They also last for different amounts of time in the atmosphere. To make it easier to make decisions and gauge the effectiveness of any particular action, scientists use the term carbon dioxide equivalent, which accounts for the different lifespans and potencies of these gases over a common time horizon, typically 100 years. For example, if 1 year of driving produces 4 tons of CO2 equivalent in a year, that doesn't mean all 4 tons of that is CO2, but it does give people a frame of reference so they can take the actions that reduce the most greenhouse gas. Next, I'll talk about some building-specific terms in the context of the BC Building Code. Absolute GHG is the amount of greenhouse gas that is emitted from a whole building in a year. Greenhouse gas intensity, or GHGI, refers to the kilograms of carbon dioxide equivalent per square meter of heated floor area. In our proposal, GHGI is most relevant for large buildings, whereas both absolute GHG and GHGI are relevant for small buildings. More details on that in the next presentation. Finally, emissions factor refers to the amount of greenhouse gas that comes from each unit of energy, which in this case is CO2e per kilowatt hour of energy. Different energy sources have different emissions factors, and the higher the emissions factor, the more emissions come from it. I realize that this may be a significant amount of information, so you don't have to memorize it all in order to be familiar with the code proposals. The terms will be used in context in the following presentations, so hopefully those examples will help you better understand how these terms are relevant. Up next, we'll go over the code proposal for Part 3 buildings. That includes the proposals for improved energy efficiency and the carbon pollution standard. If you're only interested in Part 9 buildings, skip to Episode 4. Thanks for listening. Back in a bit.